Okay, so just now if the redox one was very tough, right? Never mind. Now we are looking at gaseous state. Okay, let me just break down the topic first. Okay, then today's lesson, honestly, chill. Like you don't need to use your brain that much, but really. Okay, so you don't feel very tired. Okay, next lesson, then the second part of this chapter is going to be a bit more tiring. Okay, anyways, come, let me split the topic first. Gaseous state, right? Today we are just mainly going to discuss one thing. Okay, we're going to call this thing the ideal gas equation. So if you remember, right, okay, we just finished chem bonding. Chem bonding is very content heavy. This one is more calculation heavy. Not much content involved. Okay, so today we're going to focus on that. Next lesson, we're going to discuss real versus ideal gases. Okay, today is all about an ideal gas. The name ideal just means not realistic, right? Okay, if something is not realistic, right, some of our assumptions that we make are very easy. Okay, but next lesson we're going to look at real life gases compared to a fake gas in that sense. Okay, so next lesson is no calculations, but a lot of concept. Okay, can be a bit tricky. But today's lesson very chill. Okay, afterwards next lesson I'll do the tutorial as well. Very short topic, and then that's all there is to it, honestly. Okay, so let me just discuss a few things for today. Honestly, you just need your calculator for today, right? And then just like sub in values, this and that. Yeah, then finish already. Okay, very, very chill one. Okay, so anyways, you all can turn over to page 2. Okay, the first page. Sorry, first page. Okay, so today, right, we're going to discuss gases. Gases have properties such as pressure, volume, temperature, amount, all these things which you might have learned 2 chapters ago in mole concept. Okay, so we're going to bring it back here today. Okay, the first relationship, right, is I ask you guys, you can think of a balloon. If the volume of a balloon is bigger, right, is the pressure higher or okay, lower, right? Yeah, okay, because pressure and volume are opposites. Okay, you have squeeze the balloon, the pressure is very high. Yeah, that's the idea here. Okay, pressure and volume, in other words, are what's the relationship? Inversely proportional. Now, I just want to talk about a few things. Okay, so if you multiply by V on both sides of the equation, I will get PV proportional to 1. Agree? Now, this was a bit weird, right? Since when we got proportional to a number? Okay, whenever you're proportional to a number, right, I just need you all to go on. Okay, it means that you are equal to a constant. Okay, not equal to 1. Okay, take note. Okay, it can be equal to any number, but it just means this product is constant. Does that make sense? Sometimes you might encounter this, realize. Okay, people think that proportional to 1 means equal to 1. Not necessarily true, just means it's constant. Okay, can? So it makes sense, guys. If pressure increases, my volume must decrease such that the product remains the same, right? One go up, one go down, vice versa. Right, y'all? That's the idea here. Okay, the second gas law is this. Okay, guys. The volume of a gas is proportional to a temperature. This is very obvious. Okay, if you heat the balloon, what will happen? The balloon will expand. That's like simple physics. Honestly, guys, the first half, today's lesson, right? Not the next lesson. Today's lesson is very physics heavy. I don't know why this topic is even in the syllabus. Okay, it's very physics. Okay, so anyways, that's it. Okay, the third law, right, is volume is proportional to number of moles. I don't know why this is a law. The guy thinks he's smart. Okay, honestly, it's common sense. Okay, more amount of gas obviously means higher volume. Who doesn't know this shit? It's common sense. Okay, so this guy thinks he's so big, right? Okay, so anyways, guys, let's look at it slowly. What we're going to do now is to incorporate all these ideas together into one equation. Because if you think about these things separately, you'll go crazy. Okay, so let's try to assimilate everything. Okay, remember we learned this before. To change this into an equal sign, we must introduce a constant, right? I'll just put K for now. Make sense? Okay, and then because as I said earlier, right, P and V are together, so that you can put P equals to K. Make sense? Okay, then we just look at the third scenario. Volume is equal to Kn, right? But also volume is proportional to T, so volume is equal to Kt. And P is together with V, right? So I can like slowly combining them all together. Does that make sense? Yeah, that's how you combine ideas together. This is really that easy. So on the next page, you all can take a look. The equation we're going to use for today is PV equals to nRT. If you take physics before, it's the same exact thing. Same. Okay. The only difference here is instead of K, right, we use the constant R. So what is R? R is a constant that you need to memorize 8.31. If you somehow forget, right, what to do, look at the data booklet. Okay, data booklet got everything. Constant, I'm saying, all constant. So you forget what Avogadro's constant is, don't go and guess. Okay, just go and check your data booklet. You forget your R, just check your data booklet. It's free. Okay, so, okay, so far. All these ideas, anyone with brain can also understand. Okay, so just use this for now. Okay, so anyways, guys, now I'm going to talk about some physics stuff. If you take physics, it's going to be okay. If you don't take physics, never mind. Okay, I will explain in a more bio manner. If you all want to take physics. You take physics? Oh, you don't take physics. Yeah, okay, I don't know. Okay, so anyways, let me explain in a more friendly method. Okay, pressure must be measured in pascals. If your pressure got a lot of different shit. Okay, you all learn in secondary school also. Okay, but it must be pressure, pascals. So no matter what you do, convert to it. Okay, let me just tell you some things. If it's in atmospheres, one atmosphere is 101325 pascals. Do I need to remember this shit? Answer is no, it's in your data booklet. Okay? This is at room temperature and pressure. Room conditions. But if they give you bars is another unit of pressure, it's 100,000. Don't get the number wrong, the zeros wrong. Okay, so this is at standard temperature and pressure. All you need to do is just convert to pascals. Okay, just bear that in mind later, you're going to try the patterns. Okay, and that's it for pressure. Nothing much. Okay, I want to talk about volume. Volume is a tricky one. So I'll come back to it in a bit. But for now, right, you all need to understand volume is in meter cube. SI units meter cube. Okay, so I'll come back to that in a bit. Okay, let me talk about the rest first. Okay, guys, N is number of moles. Simple, nothing special here. Okay, you tell me temperature must be measured in what? Your physics students should know this. Kelvin, never in degrees Celsius. Okay, degrees Celsius is just more friendly to our day-to-day life. You will never have to use Fahrenheit, thank God. I don't know who the hell created Fahrenheit. That shit is ridiculous. Okay, but anyways, how do I convert degrees Celsius to Kelvin? Anyone knows? Wrong, it's plus 273. Okay, but if you go Kelvin to degrees Celsius, you minus 270. How do I memorize this shit? Very simple. C to K is alphabetical order, right? So plus. Okay, K to C is reverse alphabetical order, so you minus. Very simple. Done, I'm done. Yeah, okay, so that's it. Okay, no need Fahrenheit. Okay, so temperature must be Kelvin. I want to come back to meter cube for a moment now. Because in chemistry, right, you ever see meter cube that often? Not really. You all do your titration, you do all that shit, right? It's usually in cm cube or at most in em cube, right? You do more concept calculation mostly in em cube also. So how? We need to know conversion very well. And especially for non-physics students, this one will be a bit of a struggle. Even for physics students like me, I struggled last time. Okay, but anyways, what is 1 dm cube? How big is 1 dm cube in meter cube? We're also going to answer, well, how big is 1 cm cube in meter cube? For this, you must understand what D and C stand for. D stands for deci. C stands for centi. Deci means what? Anyone knows? Okay, I ask you centi. Centi means what? 1 meter is how many cm? 100, right? Okay, so centi is just in the power of my 2, minus 2. Okay, make sense? Okay, then deci is just minus 1, in case you didn't know. 1 decimeter. I know we never use that in real life. Okay, but anyways, yeah, can. Okay, so guys, can I ask you 1 dm cube is how many meter cube? Is it 0.1? 0.1, right? No, guys, there's a cube there, right? If you cube, then what's the power now? Minus 3. Okay, indices are math, there's no chemistry involved. Okay, but this one, if you don't get it correct, you're going to lose petty marks. It's just very sad. Okay, so, anyways, cm cube, 1 cm cube is 10 to the power minus 6. Okay, you take minus 2, then you cube it, then it's minus 6. Okay, this is not what I want to go through. Okay, what I want to go through, I'm going to give you some examples. You're going to write down all these examples and I need you all to convert. Okay, but anyways, just to be sure with this, right? Okay, we have meter cube and then we have dm cube and we have cm cube. This is the scale. Okay, the scale gets larger or smaller as you go from left to right. It gets smaller, right? Okay, bear in mind first, the scale gets smaller. Okay, so anyways, okay, go and convert let's say 17 dm cube into cm cube. Okay, and go and convert 0.14 meter cube into convert it into cm cube as well. Okay, we try these two first. Or maybe one more. 300 cm cube convert to cm. You see this plenty of times. Okay, so this one must get it correct. Stack of it. Oh, you didn't have one just now. Oh, shoot. Okay. Perhaps not. Or they need to use for maths. You need a phone calculator. Because if there's no math class going on, right, I can just take the GC. Okay, so I'll teach you my way of making this fast without doing any math. Not say any math, but very fast. Okay, so let me show you all this very quickly. Okay, if you don't know whether to divide by 1,000 times 1,000 or divide by billion, okay, that's a very common problem. Even sometimes I want to look, I also don't know. So this is how I will do it. Okay, guys, you take a look. Can I ask you all, because this is a conversion, right? The values have to be equal in magnitude, correct? So I'll ask you all, from dm cube to cm cube, right? Did the units become bigger or smaller? Smaller. If the units become smaller, the number must become bigger by how much? Bigger by? dm cube to cm cube is just a space of 1,000, right? Okay, 1,000. So meter cube to cm cube is million. You see that? So it's bigger by 1,000. So 70 times 10 to the power of 3. Make sense? If it's smaller, then you divide. Very simple. Ask you again. Meter cube to cm cube, the units become smaller, so the number must become bigger by a million. Make sense? Okay, so it's one big, then the other one, the unit must go small. It's a conversion, so the magnitude must be the same. Last one, the units are becoming bigger, so the number must become smaller by 1,000, so 10 to the power of -3. Makes sense? Then you'll never go wrong with this. Okay, we are not done. Okay, so I want you all to convert a little bit more. I'm going to convert this. For your physics calculation as well, in case you need. Because last time I also struggled with this idea. Right? Okay, so we try the first one. I want to quickly get this done and over with. Okay, anyways, meter to dm is actually bigger or smaller? Smaller, right? Okay, but because of the inverse sign, actually is getting bigger. You can see that? Okay, this is a bit tricky. The reason why I'm asking this is because sometimes they use mole per meter cube or mole per cm cube. But in chemistry, we know that it's mole per dm cube most of the time. So over here, and in this case, because sometimes we use meter cube here, there will be this kind of convergence. So anyways, meter cube to dm cube, the units are getting larger actually. So the number must be getting smaller. Smaller by 1,000 -3. Okay, Ken? You repeat the same thing for the last one. The units, okay, cm to dm is getting, without the minus, so cm to dm is getting larger, but because of the inverse, cm to dm is becoming smaller. You can see that you are like inversing the whole scale. If the unit is getting smaller, the number must get bigger by 1,000. So it should be 3.75 times 10 to the power minus 1 is bigger now, as you can see. Can see that? Yeah, look. So this is the most friendly method, whether you're a physics or bio student. Okay, can? Yes. Yes. Yes, correct. You inverse. Right. You inverse it, that means the scale is going backwards. Yeah. Okay, all good? Yeah, lor. So this is some simple stuff. Now with that said, not much for me to discuss really. Okay, maybe one more on page 4. Okay, if you never bring a data booklet, it's fine, because page 4 is in the data booklet, and you just need to refer to that. So all this atmosphere and pass and the room temperature, standard temperature, all that, right, can be found in the data booklet. In other words, okay, don't need memorize shit, lor. So you see at standard conditions, they will give you the pressure, the temperature, and the molar volume. Remember, molar volume got difference, one. Okay, it's based on this relationship here. Volume is proportional to number of moles. Why? Because the number of moles is the volume over the molar volume. As we know, this molar volume is a constant, but again, it depends on the conditions. Room temperature is 24, standard temperature is 22.7. Okay, that's pretty much it. There's nothing for me to discuss here. Okay, all good. So now that all the rules are out of the way, then we can go to the calculations. Okay, so just take your time to do that. Okay. So turn over to page 5 and 6. There are 3 questions. Let's go and try all 3. Okay, it's basically just an equation sub in value. Okay, just practice. Okay. Yeah, correct. Degree to Kelvin plus 273. As long as you get the answer on the top right, you can just move on. Just sub into your PV equals NR. One thing you can possibly do also, right, is to manipulate the subject of the equation. One thing you can choose to do also is to manipulate the subject first, right? Then you sub in the values later. So for example, here, right, I just put in the subject of the equation first, and then later I just sub in and just type it in the calculator. So I manipulate the subject. Instead of just putting the values into PV plus NRT straight up, then you still need to divide your calculator. Okay, so that's one method that I use. So, but other than that, there's nothing here for us to discuss. Q plus. Also. I feel a lot. Oh, wait. How? I thought you quit since you quit. Wait, but you're injured, right? Because of that. But if you tell your coach that you quit and then you go hockey, right? He confirm won't allow you to quit. Okay, wait, that doesn't make any sense. So if you train more, you don't get injured. Okay, I think that makes sense. Okay, wait, so you're stuck in 2 CCs. No, that one not CCA. Just go there and whack one bridge game there already. Why you 3 CCs? Pick the one, 2 of them. Oh wait, no, it's external, still need to pay, is it? Oh my god, yeah, but let's don't go already. Hockey is more fun. But you need to run a lot. That is right.
Well, I didn't know that the size of the TV was like 100 grams.
Yeah.
I didn't know that.
Yeah, almost. Alright. Your PP is going to be massively. Oh, how do you sprint 3K and sets? Oh my god, that's damn tiring. What the hell? Yeah, that's damn tiring. Get 200. Oh my gosh. Okay, done those. All done. Okay, so that was the easy part. Okay, now let's just start introducing more variables into our equation. Alright. Oh, still wait. Okay, the third question is the same thing. Then we move on first. Like I said, that's the instructions for the canvas. We have our own canvas thing already, right? Have you tried logging in? No, just like try logging in. Like if you can't log in, then you just now we just need login because we are not using it that much yet. We are still getting it ready. Eventually when we go on all the quizzes and all that, I also need your okay. Yeah, okay, the third question is the same thing. Then the one that do it. Right, let's do a bit more math. Okay, so for this part, right, what we're going to do now is just introducing more variables about gases. Okay, so for now, gases only have pressure, volume, number of moles, and temperature, right? But with a little bit of the magic of math, right? Okay, we can actually introduce more variables into the equation. We're going to introduce this, and this. Okay, 3 different variables. Okay, we go with the nodes now. Okay, the nodes only told us, the first one in our nodes was MR, right? So guys, if you want to put MR, if you want to incorporate it into this equation, right, what can we possibly do? Okay, good. Number of moles, we can change it to what? We can change number of moles to, oh, no. Okay, it's mass over MR, right? So, in this case, if you want to introduce MR, you just need to take PV equals to M over MR times RT. You can see that? So, you're expanding it into more variables. It's just math. Okay, so M divided by MR gives you number of moles, so you just introduce that. Then all you need to do afterwards, right, is MR. It's just MRT over P. That's it. So sometimes you are asked to find the molar mass of an unknown gas. So it's very useful because as long as you have the mass, the temperature, the pressure, and the volume of the gas, right, you can find the identity of that unknown gas. So that one equation is quite useful. Make sense? Yeah, so that's the first one. But first one very easy. Okay, the second one is a little bit more challenging. We are going to try to introduce this inside. Any idea what this thing is? What does this thing represent? Density. Guys, what is the formula of density? Now take note this is called rho. Rho are not letter P. So rho means I think the extra side. Okay, so because you're introducing both pressure and rho inside, right, you need to be very clear. If this one looks like P, right, they're gonna mark you wrong. Or you're just gonna confuse yourself. Okay, so rho is equal to 1. Mass over volume, good. Okay, if you look at the P equals the nRT equation, do I currently have mass inside? No, but I do have volume, right? How do I introduce mass into my equation? Same thing, right? Okay, I just do the same thing. So if you look at P equals nRT, it's now PV equals to nRT over MR. You need to make it such that M over V is on one side of the equation, so the right hand side, I just need you guys to try filling it yourself. Okay, so manipulate the equation such that rho becomes the subject. Okay, yes. Okay, point 1. I want to find how to put MR into my equation, right? I don't have MR. How do I put MR inside? It's number of moles. Because number of moles is equals to mass over MR. So that's why this part over here was initially your M. Then just switch it around. Okay, so let's talk about the second one real quick. Now this one, right, if you guys are a bit confused as to how you put the M and V on one side like this, right, okay, this is how you do it. Okay, if you want to make your life a bit easier, okay, I introduced this thing called it's a reverse cross multiplication. Okay, you want to cross multiply this first to get rid of all the fractions. And then you reintroduce the fractions, M over V, by reversing the cross multiplication. Okay, so since you want M and T, right, you're going to highlight that first. M is together with R and T, right? So to R and T, you're on top or the bottom? Bottom, right? Because R and T will cross multiply with M if you get them together. Same thing here. P times MR times V, so it's cross multiply. So now you can get your final equation. Okay, PMR over RT. That gives you your density of the gas. Okay, it's all math here. So you just need to try the third one. The third one is very simple. They want concentration. You ask yourself what concentration is first, then you just go and manipulate the PB equals the nRT equation. Okay? Mole per unit cube, yes. Okay, but here you just need to know what variables you're using. So it's number of moles over volume. So it's basically N over V. Right? After that, everything very simple. So this one should be quite simple. Okay, so once you guys are done with the third one, you can just proceed to the question. Okay, but when you do the questions, I want you to manipulate it from scratch. Because in exam, you cannot just you can't just possibly memorize the newly formed equations. So you manipulate it from scratch, so you get some practice in. Then eventually this becomes very simple. Okay, so anyways, the third one, right? You do the same reverse cross multiplication. Okay, so you have n and you have p. So same thing, n over b. N is together with R and T, so R and T to be at the bottom, such as NRT. P together with P, so you cross. So concentration is equals to P over R. Done. Then the rest of the questions you're going to try yourself. That will force you to manipulate it such that the subject of the equation is there first. Okay. So when you have the subject of the equation on the left, then all you need to do is just to plug and paste the values. Your values must make sense. The MR, you get something too big, right? That means your conversion somewhere very low. Yes. Temperature for question one. Question one should be okay, because they never give you, right? But they tell you standard temperature and pressure. So if you refer to the data booklet on that page over there, page 4, page 4 they actually tell you standard temperature. And it should be 27. Okay, so the pressure and temperature for the first question must be a standard, which you can find from the data booklet. I just want to highlight one more thing. When you calculate MR, right, it has to be 1 dp, not 3SF. Sometimes the 1 dp and 3SF they coincide, so that's fine. But if you get like for example like this, but if the MR is like something like 115.1, right? Do not round it off to 3SF because 3SF will tell you it's 115. That's not correct. Okay, it should be left with 1 dp just like this. Yeah, okay, so just bear that in mind. AR and MR must be in 1 dp. Okay, so I've included some of the conversions over here as well. Okay, cm cube to must convert to meter cube. Okay. Question 3 is the one that's a bit more vague. Okay, but still doable. Okay, remember for question 3, they ask for density. Please try to manipulate from scratch. Yes, density, everything else is 3SF, with certain exceptions like MR and AR. Yeah, so anything else just put 3SF. Okay. Okay, the final question, right? Question 3, there's something else I need you guys to do also. Okay, but just get the numerical value first. Are you all able to get 1,830? Or your 1.8 still? Okay, why? Okay, good. Okay, we take a look out, guys. When you put 18330 like that, this is what you see on the calculator. Okay, and can you all tell me what the units are? Density is mass over volume, so it should be gram per meter cube. Yes, okay, not dm cube, because I think we are very used to dm cube in chemistry. So right now, guys, if you look at this value here, again, we don't really use meter cube in chemistry. Like if you look at 1830, it's a very hard estimation. We don't know whether this value is considered big or small. Okay, so what we want to do, guys, using this value, I want you guys to convert this to over dm cube. It's something a little bit more digestible because this is when you get the value here, right? It will look a lot more normal as compared to something like 1.8 thousand, okay, 1,800. That was a bit too large, right? Okay, so I know you can count, I know you can find the concentration using the formula, but now I just want you all to work off from this because I need to train your conversion a bit. Okay. Okay, there are two things you need to convert here. Okay, this gram to mole and then meter cube to dm cube. Oh, no, it's not. I remember what is the number of moles formula? I think last time your school they teach you the triangle, right? You want to use this as you can. Okay, so this mass equals to number of moles times MR. Okay, use this. But just now you said something like number of moles is, I heard, mass times MR or something. Nah, wrong. Okay, so see, you have to convert one at a time. So gram to mole, just now you all said times M, which is wrong. Okay, so it should be divided by MR. Mass divided by MR gives you number of moles. Okay, so that's why you got that confused. Okay, so the easy part is to divide by the MR, which is 44, yes. Yeah, I know it's like you can don't even times this in the first place, I know. Okay, but for now, right, I just want to like talk about this separately. Okay, imagine they give you this value straight up, right? And then you ask to convert. Okay, so anyways, you divide by 44 is one thing, but what else do we need to do? Okay, good. So over here, right, the units by right should be getting smaller, but because of the inverse sign, the units are actually getting larger. So the number must get smaller, so you divide by 1,000. So the answer is 0.0416, right? About that. Okay, so take a look, guys. If you see your value, right, is 0.0416, is probably correct. How do you know that? Because I'm sure you've done chemistry long enough, right? To know that mole per dm cube is usually in the 0.01 to 0.1, that kind of range. Okay, have you ever seen like 10 mole per dm cube? No, not really, right? That shit is too large. Right? Okay, so if your answer somehow you get 10 or 50 or 100, right? That means your calculation somewhere went wrong. Okay, mole per dm cube usually is in this range, right? So you need to have a rough estimate, right? A rough ballpark estimate of what a correct answer looks like. This is how it looks like. So that means 1830, you can't tell whether it's correct or not, right? Because it's such a large number and the units we rarely ever use meter cube. But once you do the conversion, you realize that it actually is quite okay, quite insert. Make sense? Okay, so that's a conversion here. Alternatively, you can just use the concentration formula that we discussed earlier and then just find concentration straight up. All good? Can Okay, so anyways, with that said, right, let's go over to the third part of today. Okay, so we're done with the second part of introducing more variables. Now the third part, okay, need to kind of understand this a bit. For the lack of a better name, I'm just going to use the name used in the notes of combined gas equation. Okay, what on earth does this mean? Doesn't really mean much. Okay, so let's take a look at what's happening. Okay, the number one thing that I want to establish is this. The n is constant. Okay, what we are doing over here, right, is that we are playing around with different variables. Because there are so many variables here, right? Okay, we need to play around with the variables to see how one variable affects the other, for example. Okay, so here n is constant, right? What's going to happen? Okay, take note, right? Is equals to nRT. And we're going to identify all the constants. So if n is a constant, I'm just going to put a tick. Is there anything else that's a constant? Okay, R is a constant. So do you realize I'm just going to manipulate the equation such that all the constants are on one side of the equation. So PV divided by T equals to NR, right? So NR is basically a constant. In other words, PV over T is a constant. You can see that? Now, what does this mean? Okay, so it just looks like me doing some random mathematical calculations. Okay, but you take a look, right? What happens if, let's say, I tell you that the pressure increases? Okay, if you realize something, if the pressure increases, does the whole thing increase? Okay, by right it does, right? But you have to understand, right? It has to remain as a constant. This entire fraction over here must remain as a constant. So what else must respond to this increase in pressure such that the whole thing remains constant? Okay, volume could decrease, right? So that's one possibility. Volume can drop. Alternatively, what else can happen? Temperature can also increase to cancel out, right? So you don't really know whether it's one thing change, two things change, or both things change. Okay, it could be either one. I'm just telling you guys that these are some possibilities. If the pressure of a balloon increase, right, okay, it has to maintain the volume if you want the amount to be the same, for example. Okay, so there are many other examples. Okay, if I ask you guys if the volume decrease, right, what could possibly happen? Okay, the pressure increase actually. Okay, because one go down, the other must go up to cancel this out. How about temperature? Temperature will decrease. Okay, because yeah, it's all coming back to our relationships that we learned earlier. Okay, the last one very simple. Okay, if my temperature decreases, then what could possibly happen? Pressure will okay, if this one drop, right, it must be cancelled out with a decrease in pressure. Alternatively, my volume could also decrease as well, right? Because it's like above and below. It is just your possible relationships here. Okay, again, you don't really need to do this, just for you to understand. Okay, so yeah. What we're gonna really do is to spot questions that utilize this in exam. How do we spot this? Okay, so I want to understand. If this fraction is a constant, we can actually derive something like this. PV over T, right? If it's equal to a constant, then we can also come up with another scenario of PV over T. So if you notice what I just did over here, right? P1 V1 over T1 is equal to P2 V2 over T2. What does 1 and 2 represent? 1 represents the before and 2 represents after. Basically, if there's an initial and a final, right? Okay, the overall fraction must stay the same. Okay, but then the values can change. That's the idea here. So if we recognize that the number of moles of gas is a constant, right? Okay, this formula will usually apply. So let me show you guys for combined gas equation, I need you all to take note of two things. Number one, how do you spot this kind of thing in the exam? You must check if the number of moles is constant first. Once it is constant, right, usually you try to spot for a before and after scenario. If there's a before and after, you utilize this equation here, no? Make sense? Okay, so we look at an example first, then all the calculations you're going to do yourself. Okay, so you just turn over to page 11, right? I just need you all to read the first question. Just read like what's going on over here. So we're going to check the indicators of whether we need to use this combined gas equation. So can I ask you all, right? Is the number of moles constant in this question? How do we know that? It's common sense, right, guys? The bubble, is it like, did any extra gas go inside? No. So the amount is the same. And guys, is there a before and after scenario? Yes, right? Before is at the bottom of the ocean, afterwards is at the top. Yeah, okay. So once you can identify these two indicators, right? Just take out this combined gas equation. That's good. Then just go and calculate whatever that's necessary. Okay, there's one more thing I need to discuss, but you're going to try first. Halfway through, let me mention it. Okay, but for now, go and calculate question one. Yeah. No, the volume is not remaining the same. They never say what. The initial volume is 0.03. They want us to calculate the volume now when it's at the top of the surface. Yeah. So you can already tell that there are some variables that are changing, some that are not. Okay, they give you the pressure in atmospheres and the volume in cm cube. Yeah, let me just ask you a question since you're doing halfway now. Do we need to convert the pressure into the correct units? Why not? Because you know this is a situation that cancel out, right? So here, initial volume is 8.4. Sorry, initial pressure is 8.4. Initial volume is 0.03. Do we need to convert 0.03 to meter cube? Also no need, right? Okay, because they'll cancel out on both sides. So you do something like this. You want to find V2, that's what the question was. Guys, how about temperature? Do we need to convert? Mass. Okay, guys, take note. Why is it that pressure temperature you need? Because temperature is an additive conversion, right? Degree Celsius to Kelvin, that's not how math works. It's not multiply, it's add. So no matter what, takeaway from this question is no matter what, right, your temperature must always add up. Okay, sorry, temperature must always convert to Kelvin. Okay, then from there you can find V2. Just make sure your V2 remains consistent. If you didn't convert your cm cube, so it's still cm cube. Okay, then go and try the other two features. Okay, so it's all about saving time here. Yeah, okay, so question one also no even. Question one is cm cube. You will also remain your answer in cm cube. It's fine. You'll cancel out the conversion. Oh, good. You see, the first part of this chapter, right? I'll never revise with you guys ever again because it's damn. The only part that we will revise, right, is the last part of this chapter. Okay, for now it's just do only. None of which is even chemistry. I don't know why we're doing this, honestly. Yeah. I'll go through this once, I'll never go through this again. Not even in June when we do revision. Or maybe have till. Okay? Hello. So OG. You're doing this holiday. Why are you doing this? You're gonna fight a guy tomorrow. Yeah, what the shit's Thursday already.
Yeah.
Wow.
Damn shit.
Yeah.
Today I had my netball camp from 8 AM to 2 PM.
Who?
Netball camp.
Like just now?
Yesterday.
Oh, 8 PM to 2, 8 AM to 2 PM. So long for what?
It's like
Oh shit.
3 hours of training, then the rest is like bonding.
Bonding is just going to eat, right?
Yeah.
Shit, wow. Hopefully you can punch the guy, nice, quite fun.
Yeah.
What's the confidence of really high, right? I mean, you say you don't know shit, right? So you just feeling a little bit trapped, masculinity a bit trapped.
Depends on who's coming. It could be a fun.
Oh, you see, that's not feel that shit, that is for everyone.
Basically, my friends came over to my house, then they said,
Yeah.
he's a blur, he's a blur. Then after that, they tried to find me, right? I punched my friend until the saliva come on. He's a big guy, so I'm not worried about it.
That's funny. I thought you punch and he beats your wife. I think shit on the shield. Okay, guys, you realize our question 2, right? There's one more thing that's constant, right? Okay, your number of moles at R is constant, but they also say temperature is constant, which means to say, right, question 2, your plot is different here. It's just P equals a constant. So P1, V1 is P2, V2. So don't go and put the T inside if it's unnecessary. Okay, then yeah, that's it. Okay, then the last question is just a repeat of the first one. Okay, can? Okay, once done with this, okay, I want to, if you haven't finished the last one, never mind, it's the same shit as the first question anyway. Okay, page 13 onwards. Okay, this is where things start to ramp up in difficulty. Okay. Okay, because what we're going to do right now, okay, we are kind of done with combining gas equation. We're going to do the fourth thing, which is on graphs. So graphs is a little bit more conceptual. There's no calculations we have to perform here. Okay, so let's give this a try. Right, so when it comes to graphs, right, what must we do? Okay. Take a look. Okay, look at the first graph there. The graph that we're going to draw is PV against P. How does this graph look like? Okay, so first of all, right, we need to look at the conditions set up to us in the experiment. PV equals nRT, let's identify all the constants. They say fixed amount of gas, so N is a constant. What else? Constant temperature, and R is by default constant, right? So we have the same thing as what we got just now. PV is equals to a constant. Agreed? Then what's next? If PV is equals to constant, that means what? If you look at the axis for this graph, right, it's a bit weird because we have both PV and P, right, on like the same graph. So I'll ask you guys something. When P increases, what do you think will happen to the shape of this graph? Okay, when P increases, what will happen? V has to decrease to maintain the PV product as the same value, right? So could you possibly guess what's the shape of this graph? Thank you, bye-bye. Okay, could you guess what's the shape? So when P increases, V will decrease. So it's a straight horizontal line, right? Okay, so now you may be asking what's the point of this graph, right? Okay, never mind. In the second lesson, right, then we will look at the point of this graph. For now, there's not much for me to discuss. Okay, Ken? T? Oh, because the question says so. At constant temperature. Yeah. Okay, but there's some variations of this graph, because there's a lot of space, right? Let's draw a few more variations. Okay, so sometimes, right, you might see P against V instead. Guys, what's the shape of this graph here? Also a straight line. Honestly, it's just the same thing. So don't be surprised when you see a V instead, because it's the same idea. Okay, when V increases, right, the pressure will increase such that the product remains as the same value. Yeah, that's it. Okay, one more is like very obvious. Sometimes, right, they try to throw you guys off, because this topic is a bit simple, right? So they try to throw you off, right, by switching up the values over here. So guys, what would the shape be now? Okay, the shape will just be a straight line, as in what kind of straight line? Horizontally, should be vertically, right? Because now you just, all you're doing is just split this like 90 degrees now, then you, sometimes you get that. Yeah, this looks a bit ridiculous. But sometimes they come out with that to throw you guys off. Yeah, that's it. Can? Yeah. Okay, this one easy, let's just move on. Okay, all these graphs are not even the difficult part yet. The difficult part comes later. Okay, so can y'all take a look at the next one, right? They are talking about V against T. So the same thing, right? I'm just going to take T because NRT and go and identify all constants. The question said fixed amount of gas at fixed pressure, right? So R is also a constant, always. So the relationship here is what? V is proportional to T, right? So what should the graph look like? Okay, linear graph, okay, but that's not specific enough. It's linear to me like this, right? So this is wrong because, sorry? Start from 0 basically, passing through the origin. Okay, so guys, sometimes right, graphs, right, they will test you guys on to describe the shape. So this is a directly proportional relationship. And whenever it's directly proportional, right, you need to make sure it passes through the origin. So it's a straight line graph with positive gradient passing through the origin. Okay, let's just write the whole thing down. Because sometimes they can ask you to describe. Okay, straight line. A straight line can mean a lot of things, so it's a positive gradient. Okay, passing through origin. If you just tell me it's linear, right, it's actually wrong. Okay, I know it's linear, but not all linear graphs are directly proportional. So linear to me is just a straight line, but to be downwards also, it doesn't have to start from 0. So never ever use the word linear to describe this graph. Okay? Okay, but one more thing, let me just make this a bit smaller. Okay, now I hope you have enough space because we want to draw another graph. This graph is V against T passing through the origin. Can you tell me what's the units of T? Okay, it's in Kelvin. Can you all now try to draw a graph because all the graphs and transformation in math already, right? I hope, I don't know. Okay, but then I want you to change it to V against Celsius. Go and try. The one will come on. If V against degrees Celsius. You think of a math concept, right? All your transform this and that. Okay, this is not wrong, right? It's actually correct, but it's not complete enough. Yeah, so perhaps maybe I can give you guys a hint. How do you convert Kelvin to degrees Celsius? Degrees Celsius, if degrees Celsius is equals to Kelvin plus or minus 273? Minus, yes, okay, so take Kelvin minus 273. Basically, you're taking this graph and you're translating it to the, okay, let me go and try this out. Have you learned graphs and transformation yet? Should be, right? Yeah. One of the easiest topics. Right? Okay, but I won't use that concept. I'll use another more friendly method. Okay. Okay, but you must tell me what's the, you are starting at a point that's not 0, right? You must label what that point is. Okay, so some of your graphs are not wrong, but then it's not complete. What do I mean by that? Okay, can I ask you on the graph translate? How? How does it translate? Okay, vertically or horizontal translation. Horizontal, right? Because it's the x-axis, right? Okay, so you're shifting the graph to the left or right? Okay, left, because minus mark. Okay, the easiest way to do it is as such. Screw all the math and transformation shit. Okay, over here, guys, 0 Kelvin, right? 0 Kelvin corresponds to which degree Celsius? 0 Kelvin is negative 273. So guys, you have to understand, this is the lowest possible temperature ever. So for this volume against Kelvin graph, right, there is no negative region. No such thing as negative Kelvin. Please take note. Okay, 0 Kelvin is also known as absolute 0. It's the lowest temperature of the universe. Okay. Anyways, so the graph should look like this. Temperature in degrees Celsius, 0 Kelvin, this point must correspond to negative 270. So you must be able, you don't label is also wrong. Okay, so volume is here, and then you just go upward. So you just translated it. Okay, the reason why I say some of your answers are not complete, right? Is because you already showed me this part. Okay, it's not wrong lah, but it looks like you have translated the graph upwards also, you know. Can you all see that? To me, you guys have translated the graph upwards to an examiner, basically. Okay, but it's not like you're actually translating it to the left. So you're not wrong, but I would say it's wrong because it might be interpreted differently. Okay, the concept is that you're not translating upwards, but sideways. Okay, all good? All right, anyways, simple one, let's move on to the last graph. So the last graph is P against B. Guys, can you all just draw that yourself? Try it because I showed you all 2 questions already. Incorrect. Common mistake. Okay, there's a bit of math concept here also. Lah. If you know your graphs topic well, you should know this. Okay, go ahead and determine the relationship first. Okay, right. Olivia, yours also not correct. Okay, first of all, can someone tell me what's the relationship? Pressure and volume is inversely proportional. Okay, so let me write here, inversely proportional. Okay, and because of that, y'all would say if volume increase, pressure will go down, right? So you will give me this graph over here. You can cut the axis or whatever. But why is this wrong? Because can I ask you all, in math, right? In math, what is this graph representing? Y equals to minus x. Can you all see this is incorrect? Okay, because it's not a y equals to minus x graph. It is a y equals 1 over x graph. Do you all know what 1 over x is? Should be 1. Okay, so this one got asymptotal, remember? Okay, so this 1 over x graph, if you really forget, okay, you just go and punch your graphing calculator. Okay, but anyways, it should look like this. As B increases, P decreases, yes, but it's not a linear graph. Okay, so this is a math concept really. This is a y equals to 1 over x graph, which corresponds to your and 1 over anything. Okay, all good? However, guys, non-linear graphs are honestly not very useful. It's more difficult to interpret. Like for example, I ask you to find a gradient, it's more difficult compared to a straight line graph. Guys, is there a way, right, that I can make this a straight line graph passing through the origin? Watch right. Good. You can plot P against 1 over V. You all learned this in secondary school. Linearization of graphs. This is non-linear, this is linear. So when you linearize a graph, right, it can be interpreted in 2 ways, guys. It can be P is inversely proportional to V. But it could be P is directly proportional to 1 over V. That's how you linearize it. This is infinitely more useful. Okay, see these graphs, that's it. Variations all done. All good? Okay, that's not even the hard part yet. Okay, so let's go over to page 16 and then 17. Okay, so far, any last questions regarding graphs? Yes. It doesn't really matter actually, because if you switch to V and P, right, it's the exact same graph. Their relationship still remains inversely proportional. Yeah, you turn this graph like 90 degrees, right, you still get a curve, right? Yeah, so it doesn't matter. Yeah, okay, can your plot V against 1 over P also can same thing. Okay, good. Okay, let's move on to 16. You don't need to read now because I will tell you guys. Okay, the graphs get difficult when there are more than 2 variables. What do I mean? Turn over to page 17. Okay. Okay, guys, on page 17, you already noticed there's one problem. Okay, you have how many variables in total? Yeah, how come suddenly got 3 variables? What's going on here? So I have v against 1 over p. Now we know this is a straight line, but they gave us 2 straight lines. And why are there 2 straight lines? Because got 2 different temperatures. The question here is asking which temperature is higher, correct? How do we determine this? Okay, your school might teach you a method, but I have my own method also. But I don't want to tell you all yet. Okay, I want you to possibly think of a solution to this problem. Okay, so I ask you all again. I have 3 variables. That shit is impossible to compare. If I want to compare, I only want to compare 2 variables, right? What should I do here? Say again, I have 3 variables, but I only want to compare 2 variables. So the last variable, I need to make it what? Constant. Agree first? I make one of the variables here constant. Can I make t constant? No, right? I mean, t is obviously different. They're asking which one is higher. So obviously, t is not a constant already. It's either you make v a constant or p a constant, right? Hey, but how on earth do I do that? How do I make it a constant? Doesn't make any sense, right? How do I make p or v a constant? How? Okay, so this is the part where you guys can draw a vertical line. Can someone tell me what's the purpose of drawing this vertical line? I've given you guys the background already. What's the purpose of drawing a vertical line? Good. Guys, do you see this? Okay, if I draw a vertical line, right, I'm cutting these 2 points on the graph. I am limiting p. So you can maybe write this down. At the vertical line, right, 1 over p or just p is constant. Essentially, I fixed the problem that I sorted out just now already. Okay, I had 3 variables, but now I have reduced it to just 2 variables. So guys, what are the variables I'm comparing with? V and T only. Perfect. I solved the problem. Guys, if you don't want to draw vertical line, I want to draw horizontal line. Can or not? Can also, but what am I making constant now? V instead. I prefer vertical. I don't know. It's just I prefer this orientation. You want to draw horizontal, go ahead. Okay. Anyways, guys, take out your previous NRT equation again. Now let's just consolidate all the constant variables. As we mentioned, P is constant because I literally made it constant. Anything else? What else is constant? Now, as I mentioned, all these graphs, we assume N is constant as well. Okay, R is also a constant. Right? Okay, so we are just comparing V against T, right? So we have our relationship V proportional to T, which we have learned since the start of the question, start of the topic. So guys, look at how do we solve this question. The higher the V, the higher the T. So go back to the graph. The higher the V, see these 2 points, that means T2 must be higher. T1 lower. So the answer here, T2 over T1. All I need you all to do now is just to try the rest of the questions. It's the same freaking method. Ain't nothing special. Okay, I'm not drawing a line for fun. Is to solve a problem of having too many variables to compare. Okay. Yeah. Oh yeah, there's a typo for the last question. So T, yeah, which temperature is higher? T1 or yeah, the third question there's a typo. Third question is they're asking for temperature. Yeah. Anyways, I write down the answer for question 2 first. Okay. So to make it even shorter, right? When you draw the vertical line in question 2, you're making which variable constant? T, right? So T is constant. You're just comparing V against T. So we know P and V are inversely proportional. So the higher the V, the lower the P. So that means P2 has to be lower. What? Does that make sense? Higher the V, that means this P is lower. So P2 is lower than 1. Can? The third question is the same thing, honestly. You'll get a method. All's good. Okay, good. Oh, the typo is the question is asking for temperature. So the graph is correct. It's just the sentence is wrong. Yeah. Okay, all good. All right. We take a short break first. Okay, later we move on to the next segment. We covered most of it today already. Anyway. Okay. What's going on? Okay. Alright guys, okay, let's continue. Okay, so we're gonna talk about the one more part here. Okay, so this one has some calculations as well. Okay, so this fifth scenario we're gonna discuss today, right? It's what happens when we mix gases. Okay, mixing of gases. Okay, so let's introduce a few terms first. What is mixing of gases? Number one, partial pressure. What is the meaning of partial pressure? Do you all know? You know the pressure of a balloon, the pressure of a container, all right? Okay, but what's the partial pressure? Okay, so let me introduce a scenario, right? We have a container. Let's just say this container is full of air. But can I ask you, all right, that's only made out of oxygen? No, air is made out of, like, let's say oxygen, nitrogen, and let's say for some carbon dioxide. Assuming there's only these gases in the container, right? So how do we find the pressure of the container? The pressure of the container is because of all three gases, correct? But of course, in reality, it's because of individual gases all added up together. So what's happening is partial pressure is the pressure of an individual gas. Okay, take note of that. So when we say partial pressure, it's just the pressure of, let's say, oxygen, partial pressure of nitrogen or carbon dioxide. Okay, this one should be quite simple. Okay, but then how do we find the total pressure, right, of the container? It's actually very simple. So there's this thing called Dalton's law. This guy Dalton, right, okay, just claims that the sum of the individual partial pressures will actually add up to the total pressure. So meaning, right, now that we understand this, it's very, very simple to perform calculations. So to find the total pressure of this container, we just need to take the partial pressure of oxygen, partial pressure of nitrogen, and partial pressure of carbon dioxide. Now this is on one condition, okay? This is contingent on the fact that no reaction happens within the gases. Okay, no reaction happens between the gases. So guys, you have to understand, here oxygen, nitrogen, and carbon dioxide, they don't react on a normal basis, right? On like room conditions. So you can add up all of them together. They're just chilling. Okay, in this case, they are all independent of one another. Every gas over here is independent of one another. They're not affecting each other. They're not reacting with each other, then this condition will work. Because you have to understand, right? Let's just say in another situation in which oxygen and nitrogen will react, they need to consider mole ratio and all that stuff already, which is a lot more complicated, which we will not consider in this scenario. Okay, can? So the notes also got illustrate some diagrams over there, but I need to go over to page 21 now. We're going to derive, right, what's the formula of finding partial pressure. Okay, so it all boils down, right, to your PV equals to nRT once again. Now, if you look at this container here, right, can I ask you, okay, what's changing in this case? How do I find the partial pressure of oxygen gas? Okay, so clearly we have to have some assumptions. Okay, the temperature of the container is the same throughout. Okay, the volume of the container is also the same, right? Okay, and then R is the same because it's a constant. Here, of course, the pressure is changing because I have a different number of pressures. And the number of moles must change as well because the number of moles of every gas must be different. Right? It cannot be an equal amount, right? So that's why we can conclude that partial pressure and number of moles must be proportional. And we can actually use this relationship, right, to split it even more. So you can see the partial pressure of, let's just say, oxygen gas, right, over the total pressure. Do you all agree, right, that this fraction is equal to the number of moles of that gas over the total number of moles? The fraction is the same because they are proportional to each other. Now, the number doesn't have to be the same as the individual variables here. What do I mean? If let's just say the partial pressure of oxygen is 2, this one is 3, this one is 5, can you all see the fraction is 2 out of 10 of oxygen? But here the number of moles doesn't necessarily have to be 2 lah. Just be very clear. Only the fraction is equal. This one could be like 0.1 and 0.5 moles. They're not exactly the same value, but the fraction ends up being the same. Make sense? So with this relationship, honestly, you just need to know this. As long as you know this, right, you can find any of the 4 variables over here. But since we are interested in partial pressure, this guy, we just multiply total pressure on both sides of the equation. So you get number of moles over number of moles total, multiply by total pressure. So in other words, right, this is the formula. Now, I'm not a fan of asking you guys to memorize this formula because a lot of people don't know how this formula comes about. Then a lot of people end up forgetting. To remember it, I need to know how it comes about. So I suggest using this instead. It all comes from this relationship over here. Okay? So the main idea is that once we have all this down now, okay, I just want to introduce some terms. This is also known as mole fraction. So if the question says mole fraction, it literally means the number of moles of the gas over the total number of moles. It speaks for itself now. Okay, can? Okay, with that said, okay, you all just need to go and try the questions on the next page. Okay, these questions are not difficult, so you are not going to really come out an exam. It's the later part that I'm going to go through. So now, right, okay, try question 1 and 2. 1 is simple, 2 is a bit more tedious, but not difficult. Okay? Question 1 test your knowledge on the formula, right? So you'll never come out in exam. This question 2, they need to do a bit more work, right? It is same thing. I was just about to say that. No, but I think okay, you gotta be more specific. You don't be a malnourished dog in the streets of like the like some no. I just want to be a golden retriever, right? In a rich household. That's it. That's all I want. I don't care rich where rich care. Then they will treat you well. I don't be a big dog. Golden retriever also. Oh, serious lah. Oh, no, me a brother the same. Same exact thing. I've thought about this all the time. I just want to get golden retriever because they're so nice. Why cat? Cats are kind of dingy, you know. Yeah. Yeah, when you think of all character, like, or golden retriever, you can like hopping around. Cats got personality. Yeah, like some got temper. Yeah. Some like to do what? To make to cause much misery to the owner. Quite a cat. Wow. Bro, wait, that like what means that? Like I was wait, yeah, what lost on smart, very smart little bastard. But there it. Wow, that line like nice, and then you just sleep like that, right? Suck in like. Wow. Oh shit! How she go upstairs? Like she take the lift. Don't tell me the cat take the lift. What the shit? Wait, like by itself. So it jump up to hit the thing.
If the neighbors know we was
Oh my god, that's like cute. Man. What? Wait, do you see every book? It's damn impressive. Can I say that? Damn impressive. 40 trained animals are what? One of a kind. Wait, but how about like you have to spread things like that? Like I don't imagine the goddamn toilet bowl so big, right? And then the cat just spreading his things there. And then you don't know. It's just shitting. God damn it. He talks quite stupid, but like the good things. Okay, not smart. The German Shepherd very smart, but that one very hard to treat. But golden retriever is a dumb little boy. Very smart. I thought they're very loyal. That's it. Yeah, but they're not like intelligent kind of smart. I don't know. I don't know dogs very well. But yeah, give me. Golden retriever over there, right? That's stupid. So like. Oh, then Hula brought a dog to the center. Damn cute. Machi. Wow. I think I asked her bring again. Thank you. Yeah. For this week, I don't know about next week. Yeah, question two a bit tedious. Okay, let me just write down the answer for this one. Okay, take note, you shouldn't be calculating in mass, you should be calculating in moles because the MRs of these two gases are different. So you should be settling that first, right, before you do anything else.
Wait, until like the job class, right?
Okay, yeah, the answer is on the board. There are many ways to do this question. Okay, as long as you can get the answer. What I did is I find the total pressure first. So I add up the number of moles. Okay, so I add up the number of moles, put it in the PV because the nRT is the total pressure. And total pressure, I utilize this formula here to get the individual partial pressure. This one you just minus off from the total. Then you can get the answer. Okay, this one should be quite simple. Yeah, okay. So now, okay, this is used for next time there are more concepts that we add on to it. Okay, so for now, right, what we are mostly interested in is page 23. Okay, so this one I just need you all to read through first, because most exam questions will test you on this. Okay, so read through page 23 first. Okay, that question. Okay, then we explain what this type of question talks about. Okay. Okay, so it looks like a little bit of a mess right now, right? Okay, so we try to break this down now. Okay, I need you to take note, this page is very important. Mixing of gases, right? The main question type is when they connect different flasks together. So we call it connected flask now. Okay, for lack of a better term. Okay, you all think of it this way, we draw a diagram. Okay, this will be a lot easier. Okay, number one, we have Q. So flask Q, right, is just this thing over here. Okay, flask Q contains 1 dm cube of a gas and 2 kilopascals, right, of pressure. Okay, we just put all of that inside first. Okay, but then of course, separately we have R. Now R has 2 dm cubes, so I draw a little bit bigger, and 3 kilopascals of pressure. Now take a look, right? These are separate gases. Now there's a reason why they use, what's the gases they use? Helium and neon. What are helium and neon? They are noble gases, right? Why do we use noble gases in these kind of questions? Because when they mix together, they are inert, they don't react, right? So that's the condition for us to utilize this formula here. If you want to sum up all the individual partial pressures, remember what I said just now, you need to ensure that there's no reaction. Now, some questions they can test for reaction, but they want to give you more information. We stick with the basics first. Now, can you all see there are two separate flasks? They're not even related. But then now they say the flasks are going to get connected while maintaining at constant temperature. Let's see what's happening here. When they connect the flask, right, can you all tell me what's happening? So let's just open up a valve over here. Okay. Now, initially, gas Q occupies here only, right? Now it occupies what? After you connect them. It occupies the whole system, you can see that? Because that's how gases work. It just spreads itself out across the space it's enclosed in. Same thing for this guy, it will spread out, right? Okay, so look at what the question is asking for. They want the final pressure of the system. To find the final pressure, what do we do? Based on what we learned in this segment, the final pressure of the whole system is you take what plus what? Okay, sum of the gas Q and gas R, right? So you take the final pressure of Q plus the final pressure of R. You add them up together. Okay, so that's what we're eventually going to do. So we need to find the individual partial pressures first. But how do we do that? Is it 2 plus 3? Yeah, 2 plus 3. Correct, right? You connect them together, just add them together. Can we do that? Why not? Guys, when gas Q occupies a larger volume, the pressure must drop. So it's not going to be 2. You need to calculate the value. So guys, what equation allows us to calculate the Q partial pressure? There's some sort of equation that we have learned earlier. What can we use? Okay, guys, if you all notice, can I ask you number one? Is the number of moles of gas constant after the connection? Yes, right? I mean, you're not adding any more gas inside. Okay, and number two, is there a before and after scenario? Yes. You'll notice that before you connect, so it only occupies this space. After you connect, it occupies the whole thing. So what's the equation that I can use here? What do we use earlier on? This is the combined gas equation. What was the combined gas equation? What was it about? Okay, first of all, you need to identify all the constants, right? So PV equals nRT again. Okay. What is constant? Is temperature constant? Yes, they say it's constant, right? Okay, R is constant, obviously. Is N constant? Yes, we just mentioned it's constant. Is volume constant? No, right? Because there's a before it's only like that, after it's so much bigger. Okay, is P constant? No, because we know that as the volume change, the pressure will also change. So in other words, this is a situation in which P equals the constant. So guys, what's the formula we can use now for to incorporate before and after? P1 V1 before equals to P2 V2. Now guys, take note. This is just to calculate gas Q. Okay, so remove this. This is just to calculate gas Q. So let's sum in the before and the after. But after you're done with gas Q, you all notice you need to repeat the same thing for gas R. Also do P1 V1 equals to P2 V2. So you need to repeat this twice because you're finding two partial pressures and then later you just add them up together. So I need you all to sum it in and then that's the method for this question. So you notice there's an application of two things here. Number one, combined gas equation. Number two, the mixing of gases, the partial pressure concept. Two of these concepts can give you this connected flask scenario. This is very commonly tested in exam. So that's why I explain the logic first. Okay? In example, you draw it out also. If you don't draw this out in exam, right, it's a bit hard to see also, right? All good. Okay, so to reiterate, these kind of questions are calculate them separately first, two separate partial pressures, then you add them up at the end. Okay, you can add them up because they don't react, they're either gases. Okay. Okay, so P1 for Q is 2. Okay, you can maintain as kilopascals, you can maintain as dm cube because they will cancel. Volume was initially 1, but the volume now is 3. Partial pressure is 0.67 kilopascals. Repeat the same thing here. Pressure is 3, volume is 2, and then volume is 3. So the final partial pressure of R is 2. Add them up, 2.67. Can see that? All good? Okay, so any final questions here? No, okay, so that's pretty much it for today. We've covered everything we've covered already. Because next lesson, then we will start to talk about, if you look at the next page, right? We will talk about real versus ideal gases. Here, this is the end of calculation already. Next lesson, we're going to understand there's some chem bonding stuff back inside. So very, very conceptual. Once I've covered that, right, please remember to bring the tutorial as well. We're going to try tutorial questions. Okay, this topic quite important for the last part. Okay, so today's lesson pretty chill, okay, all calculations. Right? Okay.